So imagine you were just sitting on your couch, right? You're browsing Amazon on your laptop, looking for, say, a new pair of hiking boots.
Okay, yeah.
You click on a few options, maybe read a review or two, but you don't actually buy anything. You just close the laptop.
Right.
But then like 10 minutes later, you pull out your smartphone while you're waiting in line for coffee. You open up your social media feed, and suddenly you are absolutely flooded with ads from REI, Carhartt, Timberland.
Oh, yeah, it happens all the time.
It feels eerie, right?
Yeah.
Like someone is literally looking over your shoulder. And then later that night, you decide to unwind. Start watching a movie on your smart TV in the living room.
Sounds relaxing.
Right. But halfway through, you realize you're just too tired to sit up. So you head to bed, grab your tablet, open the exact same streaming app, and you seamlessly pick up that movie down to the precise millisecond you paused it.
It's pretty wild when you actually think about it.
It is. How is this invisible, ubiquitous web of connections actually operating behind the scenes? And, I mean, why does it always feel like the infrastructure itself is just tracking your every move?
Well, honestly, it feels that way because it is explicitly designed to do exactly that.
Wait, really? Deliberately?
Oh, absolutely. I mean, we experience the polished, magical front end of these systems every single day. But the underlying infrastructure, the massive physical cables, the cellular handoffs, the actual data routing protocols, all of that is deliberately hidden from the consumer.
Makes sense. You just want it to work.
Exactly. But for anyone running a business, remaining ignorant of that invisible architecture is just a massive liability.
That is the perfect jumping off point. Welcome to Managing the Future. This is our MIS Deep Dive, tailored specifically for the undergraduate business majors and the working professionals at the Dr. Sam Pack College of Business at Tarleton State University.
Great to be here.
Our mission today is to really pull back the curtain on Module 6, which is all about computer networks and the internet. And we are drawing our core framework and insights exclusively from ConnectMaster Management Information Systems by Richard Tedman and Casey Wilhelm. This is the 2026 edition from McGraw-Hill.
Yep, that's the one.
We're going to completely demystify this vast network infrastructure that makes modern global business possible.
But, before we start laying the cables for today's discussion, we really need to bridge this to our last deep dive into Module 5.
Right, which focused entirely on cybersecurity.
Exactly. We spent a lot of time analyzing the CIA triad.
Confidentiality, integrity, and availability.
You got it. And we unpacked the NIST framework, which, guides organizations through identifying, protecting, detecting, responding to, and recovering from threats.
Yeah, we focused heavily on external threats in that module. Like, we looked at distributed denial of service attacks designed to overwhelm systems.
The DDoS attacks, right.
Right. And ransomware encrypting vital data, man-in-the-middle attacks, intercepting communications. We really went deep into the plan, protect, respond cycle and how to secure data, whether it's in transit, sitting at rest, or being actively processed.
And so the crucial bridge here is that every single one of those cybersecurity threats, and honestly, the massive corporate efforts required to defend against them, they only exist because our digital devices are relentlessly communicating with each other.
That's a great point. If they weren't talking, there'd be no way in.
Exactly. If cybersecurity is the armor, today we are mapping out the massive global highway system that those shields are meant to protect. I mean, a business manager cannot effectively secure a perimeter if they don't even understand how the roads leading into their headquarters are paved.
So true. Well, if you want to keep navigating these roads with us, take a quick second to like, subscribe, follow, and share this deep dive. Dropping a comment below is honestly the best way to join the ongoing conversation with your fellow Tarleton State students and professionals.
All right, let's start scaling this architecture from the ground up. The foundation of the internet isn't, some abstract cloud.
Right.
It begins with the concept of a computer network. And stripped of all the jargon, a network is simply two or more devices connected to exchange information and share resources.
Okay, so let's apply that to my hiking boots scenario.
Right.
When I'm on the couch searching for boots, I might have my wireless headphones on, listening to music from my phone via Bluetooth.
Yep.
So that incredibly localized connection, just a few feet around my body, that's a PAN.
Right.
A personal area network.
Precisely. That is your PAN, and that PAN is operating within a slightly larger ecosystem. Like your laptop and your phone are both likely connected to your home Wi-Fi router.
Yeah, definitely.
That creates a LAN, a local area network. A LAN connects devices at a single site. So it could be your house, maybe a single office building, or even a local retail store.
Okay, so it's geographically contained.
Very contained. And the communication on these local networks is standardized. The Institute of Electrical and Electronics Engineers created the IE 802 standards specifically for this.
That's a mouthful.
It is, but it's important. It's so that a laptop manufactured by one company can seamlessly talk to a router manufactured by another, whether they are using, physical Ethernet cables or just wireless Wi-Fi signals.
Okay, but a local network is isolated. I mean, if Amazon only had a LAN in their Seattle headquarters, I wouldn't be able to buy boots from my house in Texas.
Exactly, which necessitates the WAN, the Wide Area Network. A WAN connects multiple geographic locations across vast distances.
Because Amazon can't just run a really, really long Ethernet cord to my house.
Right, physically impossible.
Right.
So businesses rely on leased data circuits provided by major telecommunications carriers, and they utilize specialized routing hardware from vendors like Cisco Systems to manage those, long-distance secure connections.
This actually introduces a terminology issue that I think trips up almost everyone. People use the word internet as a catch-all for everything. Right. But there's a massive architectural difference between an internet with a lowercase I and the internet with an uppercase I.
Oh, it is a vital distinction, especially for IT managers. An internet, lowercase I, is just a generic term for a network of networks.
Right.
Anytime you connect two or more LANs or WANs together, you have technically created an internet. So a massive multinational corporation might have a highly complex private internal internet that connects all of its global offices.
And it could be completely walled off from the outside world.
Exactly. Completely private.
So then the uppercase I internet is just the biggest possible version of that concept?
That's it. It is the world's largest internet. It's a sprawling global network of networks tied together by these immense fiber optic cables running under the oceans and across continents, which we call the internet backbone.
So why does a manager need to care about all these acronyms?
Well, the business relevance here is all about scale, capability, and cost. Like, if you are managing a single boutique clothing store, your point-of-sale systems just need a reliable LAN.
Right, it's just in the one building.
Yeah, it is contained and highly controllable. But the moment you expand into a multinational enterprise, your operations require a WAN.
You're suddenly dealing with global telecom vendors.
You are. And complex routing hardware and significantly higher security vulnerabilities because your proprietary corporate data is traversing vast geographic distances. You just have to understand these structural scales to make informed strategic decisions about your IT budget.
I feel like a helpful way to conceptualize this is through a physical infrastructure analogy.
Okay, I like analogies.
So a PAN is your private driveway, a LAN is your local neighborhood street, a WAN is the state highway system connecting different cities together. And the internet, capital I, is the global network of all interconnected interstates, international shipping lanes, and global flight paths.
That's a really solid way to look at it. But, to get your car out of your driveway and onto that global interstate, you need an on-ramp.
Oh.
That is the role of an ISP, an internet service provider. They are the gateway. You pay them a subscription fee, and in exchange, they provide the physical connection to the internet backbone and assign your device a temporary identity so it can actually navigate the traffic.
And that identity is the IP address. If we stick to the road analogy, the IP address is quite literally the mailing address for your digital device.
Exactly.
IP stands for Internet Protocol, and it is a unique numerical identifier assigned to every single device connected to a network. Because without it, the network wouldn't know where to deliver the data you requested.
Right, and there is a critical management decision regarding how these addresses are actually deployed. We categorize them as either static or dynamic.
Okay.
A static IP address is permanent. It does not change unless the network administrator manually reconfigures it.
But why would a business want that? I mean, if I'm a consumer, I don't care what my IP address is, as long as my Netflix works.
Consumers absolutely don't care, but a business absolutely must care. If your company hosts its own email server or, its primary e-commerce website, you need a static IP.
So people can find you.
Yes. Your customers and your remote employees need a reliable, unchanging digital location to send their requests to. If your web server's address changed every single day, your customers' web browsers would constantly fail to find your site.
That makes total sense. And that explains why the rest of us just use dynamic IP addresses.
Right.
Like when I connect my phone to the Wi-Fi at a coffee shop, the ISP assigns me a dynamic IP temporarily from a pool of available addresses. And the moment I disconnect and walk out the door, that address goes right back into the pool for the next customer to use.
And that pooling mechanism, it was honestly a survival tactic because of a massive architectural limitation we ran into. Historically, the internet operated on IPv4, which was a formatting standard that allowed for approximately 4 billion unique addresses.
4 billion sounds like a lot until you realize there are over 8 billion people on the planet.
Right.
And most of us carry a smartphone, wear a smartwatch, work on a laptop, and have a smart TV at home. I mean, we mathematically exhausted 4 billion addresses years ago.
We did. The exhaustion of IPv4 forced this massive transition to IPv6. And IPv6 uses a significantly longer, more complex hexadecimal string.
I've seen those. They look like a random string of letters and numbers.
Yeah, they do. But the sheer scale of the upgrade is difficult to comprehend. IPv6 can accommodate roughly 340 undecillion addresses.
Okay, wait. 340 undecillion? That is 340 followed by 36 zeros.
It's massive.
It guarantees that every single light bulb, refrigerator, and sensor manufactured for the next 1,000 years can have its own permanent unique address in the network.
Precisely. But, assigning an address is just the prerequisite. How do all these disparate devices actually format and exchange the data so they understand each other?
That brings us to the Universal Rulebook, right?
Yeah.
TCP/IP, which stands for Transmission Control Protocol and Internet Protocol.
That's the one. This is the foundational suite of standards that dictates exactly how data is chopped up, routed, and reassembled across the internet.
And it is segmented into 4 distinct layers. I really want to break these down because it completely demystifies how my search for hiking boots actually makes it to Amazon's servers.
Sure, let's do it. The foundation is the network access layer. This deals with the physical reality of the connection.
The actual hardware.
Right. It handles the electrical signals moving across the copper wire, the light pulses in the fiber optic cables, or the radio waves traveling from your phone's antenna.
Okay, so moving up one step, we hit the internet layer. This is like the routing department, right?
Exactly.
Yeah.
Its entire job is to look at the IP addresses and figure out how to move the data packets across the massive network of networks to their final destination.
Got it.
The third layer is the transport layer, and this is where TCP really does its heavy lifting. It takes a large file and chops it up into tiny, manageable segments called packets.
And crucially, it manages the reliability of the connection, doesn't it?
It does. It requires the receiving device to send back an acknowledgement that the packet arrived intact. If a packet gets lost, the transport layer notices the missing acknowledgement and resends it.
That's smart. And finally, sitting at the very top is the application layer.
Yep.
This is the only layer the user actually interacts with. It's the web browser, the email client, or the streaming app, rendering the data into something a human can actually understand.
You can visualize this entire process using a logistics analogy. Think about shipping a physical product via UPS.
I actually love the UPS analogy because it makes the 4 layers incredibly tangible. Let's say I am sending a heavy engine block to a mechanic.
Okay.
The first step is assembly. I cannot just throw a greasy engine block into a UPS truck. I have to put it in a specific cardboard box, pack it with foam, tape it shut. In TCP/IP, the software takes your digital data and assembles it into a standardized data packet.
But an unmarked box goes nowhere. You need the addressing phase. With UPS, you look up the mechanic's street address. On the internet, humans don't use IP addresses, right? We use domain names like Amazon.com.
It would be terrible to have to memorize IP addresses.
Oh, it would be impossible. So the system uses DNS, the domain name system, which basically acts like a massive digital phone book. It translates the human-readable domain name into the specific machine-readable IP address and slaps that digital address on your packet.
Perfect. So next is the shipping label. When you drop that box at UPS, their internal logistics systems apply tracking numbers, routing codes, and handling instructions to ensure delivery protocols are met.
Right.
TCP acts as that digital shipping label, ensuring all the transmission rules are strictly followed so the packet arrives uncorrupted.
And then the final phase is the actual transport. Your physical box gets thrown onto a truck, routed to a local sorting facility, maybe put on an airplane, and then onto another truck.
Taking whatever route is best that day.
Exactly. It takes whatever route is fastest on that specific day, based on traffic and weather. The internet operates the exact same way using hardware devices called routers. Your digital packet hops from network to network, constantly reading the IP address and dynamically calculating the absolute fastest path to the destination server.
I think the craziest part of this architecture is that if I send a large high-definition photo, the transport layer breaks it down into thousands of separate packets.
It does.
And because internet traffic changes by the millisecond, packet number 1 might route through a cable in New York, while packet number 2 routes through a satellite link over Chicago.
Yeah, totally different path.
And they arrive at the destination at different times, completely out of order, and the transport layer of the destination just painstakingly reassembles them back into a perfect photograph.
It is organized chaos, and it happens billions of times a second. But I do want to clarify a massive point of confusion here. We just described how data moves across the internet, but people routinely use the terms internet and World Wide Web interchangeably as if they are the exact same thing.
Which they are not.
No.
I am totally guilty of doing that myself. If the internet is the highway system we just described, what exactly is the web?
The World Wide Web is just one specific application running on top of that highway infrastructure. It is the delivery trucks using the roads.
Okay.
The internet is the physical layer of cables, routers, and TCP/IP protocols. The web is simply a massive collection of interconnected documents and media designed to be viewed in a web browser.
If the web is just the delivery trucks, there must be other types of vehicles using the internet highway.
A prime example is FTP, File Transfer Protocol. Businesses use FTP to move massive raw data files directly between servers, bypassing web browsers entirely.
Oh, interesting.
Another critical example is EFT, Electronic Funds Transfer. When your corporate payroll department initiates a direct deposit into your checking account, that highly secure financial data traverses the internet backbone, but it never interacts with the World Wide Web.
Okay, so when we are specifically interacting with the web, browsing Amazon for those boots, we are relying on a completely different set of mechanics. We have to look at HTTP, URLs, and HTML.
Right, so HTTP stands for Hypertext Transfer Protocol. If TCP/IP is the rulebook for moving raw data across the network, HTTP is the specific rulebook governing how a client, like your laptop's browser, requests a web page and how the web server formats and sends that page back.
And the address we type into the browser is the URL, right?
Yeah.
The Uniform Resource Locator. I always thought a URL was just the domain name, but it is actually highly structured.
It is.
It starts with the protocol, usually HTTP or the secured version HTTPS. Then you have the www indicating the World Wide Web Service. Then comes the actual domain name, like mheducation.com.
Right. And once the browser locates that domain and receives the data, it uses HTML hypertext markup language.
Right.
HTML is the publishing format. It doesn't move the data. It simply tells your browser how to visually render the text, where to place the images, and how to format the links on your screen so it actually looks like a cohesive web page rather than just a wall of code.
The way we interact with HTML and the web has drastically changed over my lifetime. We categorize this evolution into distinct phases.
Yeah.
Like we started with Web 1.0, which was essentially just static brochures online.
Exactly, read only.
You read it, and that was it. But the major shift happened with Web 2.0.
Web 2.0 fundamentally changed the business model of the internet by shifting the focus to interactivity and user participation. It wasn't about consuming static content anymore. It was about users generating the content.
Social media is the obvious example there, but the business application goes much deeper. A key concept here is folksonomy. In a traditional corporate structure, management classifies information top-down. But in a folksonomy, the users classify the information collaboratively, bottom-up.
And the perfect example of that is the hashtag.
Oh, right?
I mean, nobody at Twitter or Instagram sat down and coded a directory of every possible human interest. The users organically created the hashtag hiking boots tag, effectively organizing the world's data through collective tagging.
That's so true.
Web 2.0 is also characterized by the explosive growth of SaaS, software as a service, where applications are hosted in the cloud and accessed via a browser rather than installed on a local hard drive.
Which brings us to the bleeding edge, Web 3.0. How does this next generation alter the landscape for businesses?
Web 3.0 is a complete paradigm shift toward ubiquitous computing. It means computing power is no longer confined to laptops and phones. It is embedded in everything.
Really everything.
Yeah. It is heavily defined by the integration of 3D immersive graphics, deep integration with artificial intelligence, and the foundational rollout of the IoT, the Internet of Things.
So let's talk about the physical constraints of ubiquitous computing. If everything is connected all the time, we are heavily reliant on mobility. We need to leave the Ethernet cables behind.
Right.
Let's break down how cellular networks actually function, because I think most people would be shocked to learn that a $1,000 smartphone is basically just a highly sophisticated two-way radio.
From an engineering perspective, that is exactly what it is. It contains a radio transmitter and a receiver. When you leave your house and your phone drops its LAN Wi-Fi connection, it immediately starts hunting for a cellular radio signal.
Right.
It connects to a BTS, a base transceiver station. This is the actual hardware, the antennas and equipment located at the nearest cell tower.
But the tower itself doesn't know where my friend's phone is when I try to call them, does it?
No, not at all. The BTS is just a relay. It forwards your signal to a mobile switching station, or MSS. The MSS is the central brain of the regional cellular network. It identifies your phone, verifies your account status, locates the specific cell tower nearest to the person you are calling, and routes the connection to their phone, seamlessly transferring the signal from tower to tower as you drive down the highway.
There is a translation problem here, though. Human voices are analog sound waves. Network infrastructure only understands binary digital data, just ones and zeros. How does my analog voice travel over a digital network?
That requires two critical components inside the handset. First is the ADC, the analog digital converter. As you speak into the microphone, the ADC instantly translates the fluctuating analog sound waves of your voice into a stream of binary digital data.
And then the second component cleans it up, right?
Yes.
The DSP, the digital signal processor, that's a dedicated chip inside the phone. It actively filters out the background noise of the coffee shop, moderates the volume levels, and compresses the digital signal so it requires less bandwidth to transmit, ensuring your voice sounds distinct and clear on the receiving end.
And, the combination of ubiquitous cellular connectivity and digital processing allows businesses to leverage physical location in real time. This is the domain of GIS, Geographic Information Systems.
GIS is fascinating because it visualizes data geographically. It is built entirely on the back of GPS, the Global Positioning System, which relies on a constellation of at least 24 satellites orbiting the Earth to triangulate the exact spatial location of receiver.
While consumers use GPS to get driving directions, businesses use GIS to make high-level strategic decisions. GIS software captures, analyzes, and manages spatial and geographic data, overlaying it with complex business intelligence.
Let's apply GIS to a concrete business scenario. Imagine you are the regional manager for that outdoor retailer, REI.
Yep.
You need to decide where to open your next brick-and-mortar store in Texas. You don't just throw a dart at a map. You pull up GIS density and quantity maps. You layer demographic data, like income levels, age, interest in outdoor activities, over a physical map of the state.
Right, you build a picture.
Then you overlay the purchasing history from your e-commerce site, tracking exactly which zip codes are ordering the most hiking boots.
And the GIS system visualizes this complex data.
Yeah.
You might look at the map and clearly see a massive heat map of target demographics and online sales densely clustered in a 10-mile radius.
Right.
But when you check the quantity layer, you have 0 physical store locations in that zone. The GIS data removes the intuition and guesswork, allowing for optimal, mathematically sound store placement and highly targeted regional marketing.
This level of real-time geospatial tracking becomes exponentially more complex when we loop back to Web 3.0 and the Internet of Things.
Oh, absolutely.
IoT is the reality that billions of everyday physical objects, shipping containers, factory robots, even the inventory tags on those hiking boots, are now connected to the Internet, constantly gathering and transmitting data.
Yeah, everything is online.
My question is, why do we need a completely new cellular infrastructure for this? We have 4G. It streams 4K video to my phone, perfectly fine. Why is the telecom industry spending billions deploying 5G?
It is fundamentally an issue of physics and bandwidth capacity. 4G simply cannot handle the sheer volume of connections required by the IoT. 5G solves this by utilizing higher frequency radio waves.
Okay.
It offers massive improvements in capacity, meaning millions of devices can connect simultaneously in a small geographic area without overwhelming the tower. It also offers incredible download speeds, up to 10 gigabits per second.
But speed isn't the most critical factor for businesses deploying IoT, is it? It is about latency.
Precisely. Latency is the lag time, the physical time it takes for a data packet to travel from a device to the server and back to the device with an instruction.
Right.
On a 4G network, you might experience a half-second of latency. When you click play on a movie, a half-second delay is imperceptible. But considering a business-critical application of IoT on a 5G network, a fleet of autonomous semi-trucks navigating a congested highway, or a fully automated robotic arm working alongside humans on a factory floor.
If a child runs into the street, the autonomous car's sensors detect it instantly. If it relies on a 4G network to send that data to a cloud server to calculate the braking trajectory, that half second of latency means the car travels another 40 feet before the brakes engage.
And that is the difference between a safe stop and a catastrophe. 5G infrastructure reduces latency to a few milliseconds. It is the foundational requirement to make the automated, instantaneous decisions promised by Web 3.0 and the IoT physically safe and functionally viable in the real world.
This brings us to a massive shift in IT strategy. If we have billions of devices generating zettabytes of data, where does a business actually store and process all of it? They don't buy millions of hard drives anymore.
No, definitely not.
They use cloud computing, which is arguably the ultimate business multiplier of our era.
The adoption statistics prove it. Over 96% of organizations in the U.S. utilize cloud computing. It is a model where processing power, data storage, and software applications are not housed locally on a company's internal servers, but are instead provided as a service over a network, overwhelmingly the internet.
So the data from my hiking boots isn't sitting on a server in the back room of an REI store. It is sitting in a massive, centralized data center owned by Amazon or Microsoft, and REI just rents the space.
Exactly.
To truly understand what constitutes the cloud, we need to look at the National Institute of Standards and Technology. NIST identifies 5 essential defining characteristics of cloud computing.
Let's analyze them from a management perspective.
Sure.
The first characteristic is on-demand self-service. This means a business consumer can provision additional computing capabilities, more server time, extra network storage, automatically through a web portal without needing to interact with a human representative at the provider.
The second is broad network access. The cloud resources must be universally available over the network and accessible through standard mechanisms. An employee should be able to access the corporate cloud from a desktop in the office, a tablet on a plane, or a smartphone in a coffee shop without requiring specialized proprietary hardware.
Third is resource pooling. This is the economic engine of the cloud.
How so?
It operates on a multi-tenant model. The provider pools their massive computing resources, thousands of physical servers, to serve multiple different corporate customers simultaneously. The provider dynamically assigns and reassigns physical and virtual memory based on demand, second by second. The customer generally has no idea exactly which physical server their data is actually sitting on.
Fourth is rapid elasticity, which I think is the most critical for fluctuating business cycles. Elasticity means computing capabilities can be scaled up instantly and just as quickly scaled back down.
Yeah, think about retail. If you are an e-commerce retailer running your own physical servers, you have to buy enough servers to handle the traffic of Black Friday.
Right.
But for the other 364 days of the year, those expensive servers just sit idle, depreciating in value and consuming electricity. With rapid elasticity in the cloud, you instantly provision 10 times your normal server capacity on Thanksgiving night, handle the massive Black Friday traffic spike, and then release those resources back to the provider on Saturday morning.
Which perfectly sets up the fifth characteristic, measured service. Because the cloud provider is constantly monitoring and controlling resource usage, the billing model shifts from a capital expenditure, like buying hardware, to an operational expenditure. You pay exactly for what you use, metered by the gigabyte or the hour, exactly like you pay your municipal water or electricity bill.
When you synthesize those 5 characteristics, the business relevance is undeniable. Managers pivot to the cloud for massive cost savings on IT infrastructure. They eliminate the need to power and cool physical server rooms, and they drastically improve global collaboration.
That's huge.
Furthermore, it builds inherent disaster recovery into the business model because reputable cloud providers replicate and store data redundantly across multiple geographic locations.
I don't want to paint this as entirely utopian, though. The risk profile shifts dramatically when you move to the cloud. You are entirely dependent on your internet connection. If your ISP suffers an outage or a backhoe cuts a fiber line down the street, your entire business grinds to a halt because you cannot access your software or data. You also risk vendor lock-in, where a cloud provider makes their systems so proprietary that it becomes technically and financially devastating to try and migrate your data to a competitor.
And fundamentally, you are relinquishing physical control over your proprietary data. You have to trust the provider's security architecture. Because data sensitivity varies, businesses utilize 4 different deployment models to mitigate risk.
Let's map those out. The first is the private cloud. In this model, the cloud infrastructure is provisioned for the exclusive use of a single organization.
Right.
It might be owned and managed by the organization itself or by a third party. But the hardware is not shared with anyone else. It offers the highest security and control, but it is by far the most expensive option.
A step down in exclusivity is the community cloud. This infrastructure is shared by a specific community of organizations that have aligned security, compliance, or mission requirements.
Like hospitals.
Exactly. A consortium of regional banks or a network of allied hospitals might share a community cloud to securely exchange financial or patient data without exposing it to the general public internet.
Then we have the public cloud. This is what most people interact with daily. The infrastructure is provisioned for open use by the general public or broad industry groups. It is owned, managed, and operated by massive entities like Amazon Web Services or Google.
Yeah.
It is highly scalable and cost-effective. But you are operating in a shared, multi-tenant environment.
Because no single model is perfect, enterprise businesses almost universally adopt the hybrid cloud. This is a deliberate architectural combination of two or more distinct cloud infrastructures.
Okay, like mixing private and public.
Say, a private and a public cloud that remain unique entities but are bound together by standardized technology.
The hybrid model makes total strategic sense. Like, if I am a global bank, I keep my highly sensitive customer financial records locked down on an expensive, highly secure on-premise private cloud. But I host my public-facing marketing website and my employee email servers on a cheaper, infinitely scalable public cloud.
Exactly. Once a business chooses a deployment model, they have to decide what specific services they want the provider to handle. We categorize these into different as-a-service models.
These acronyms get thrown around constantly. SaaS, PaaS, IaaS. Let's start with SaaS, Software as a Service. This is the most prevalent. In the SaaS model, the vendor hosts the complete software application on their cloud infrastructure.
Yep.
The business user simply accesses it via a standard web browser. You don't buy physical disks, you don't install software on your local hard drive, and you don't worry about pushing updates.
Microsoft 365, Google Workspace, and Salesforce are prime examples. SaaS is incredibly attractive for small to medium businesses because it requires virtually zero internal IT support to maintain. The provider handles all the patching, security, and hosting.
Moving down a layer, we have PaaS, Platform as a Service. This model is aimed specifically at software developers. Instead of providing a finished application, the provider offers the underlying hardware and the software tools needed to build new applications.
The provider manages the servers, the operating systems, and the network, while providing developers with software development kits or SDKs, testing environments, and database management systems.
Okay, I like to think of it like this. If SaaS is renting a finished house, PaaS is renting a fully stocked workshop with all the power tools you need to build your own furniture without having to maintain the tools yourself.
That's a perfect analogy. And the most foundational layer is ISS, Infrastructure as a Service. This is where an organization essentially just rents raw computing power. Instead of buying physical servers, racks, and data center space, they rent the processing power, network capability, and data storage from a vendor like Microsoft Azure or AWS.
With IaaS, the vendor manages the raw physical hardware, but the renting organization is entirely responsible for installing their own operating systems, managing their databases, and configuring their own security firewalls.
But, the textbook highlights an even newer evolution: serverless computing.
To me, this name sounds completely contradictory, that physically have to be servers somewhere running the code, right?
Physical servers absolutely still exist in serverless computing. It is a bit of a misnomer. What serverless actually means is that the software developer never has to think about, provision, or manage the server at all.
Oh, I see.
In an IaaS model, a developer has to say, I need to spin up 3 virtual servers to run this code. In a serverless model, the developer simply uploads their code. The cloud vendor's infrastructure automatically executes that code in response to specific triggers or events, instantly allocating the exact amount of compute power needed for that split second and then spinning it back down.
It's like getting into a self-driving taxi. You don't own the car, you don't care about the engine specs, and you don't even have to drive. You just care that it takes your code to the destination automatically.
Exactly.
Services like AWS Lambda for executing code, Amazon S3 for dynamic data storage, and Amazon DynamoDB for database services operate on this principle. The business focuses 100% of its resources on writing brilliant code rather than managing infrastructure.
Which really forces us to loop back to our cybersecurity discussion from Module 5. When a business pushes all of its operations, data, and software into a public cloud environment managed by a third party, the security perimeter becomes incredibly porous.
This is why the SLA, the Service Level Agreement, is the most important document the IT manager will sign. When negotiating with a cloud provider, you cannot just trust that they are secure. You have to legally mandate the security protocols. Like, what are their specific disaster recovery timelines if a data center burns down? Are they fully compliant with federal regulations like HIPAA for healthcare data? How exactly is our proprietary corporate data physically or logically separated from the data of our competitors sitting on the exact same multi-tenant server?
Yeah.
What level of encryption are they utilizing at rest?
And that encryption has to extend to data in transit. Consider a modern remote workforce. If you have an employee sitting in an airport terminal connecting to the corporate private cloud over an unsecured public Wi-Fi network, they are highly vulnerable to those man-in-the-middle attacks we discussed. They absolutely must use a VPN, a virtual private network.
I use a VPN constantly, but visualizing how it works helps clarify its importance. A VPN essentially carves a secure encrypted tunnel right through the middle of the chaotic, unsafe public internet. When the remote employee sends a data packet, the VPN software encrypts the contents. Even if a malicious actor on that public airport Wi-Fi intercepts the packet, all they see is scrambled, unreadable garbage. The data can only be decrypted by the cryptographic key held at the corporate server at the end of the tunnel. It's a mandatory application-level security tool deployed to protect data as it traverses the physical network layer.
Speaking of cryptographic security traversing networks, we need to examine a technology that utilizes these concepts but applies them to decentralized trust. Blockchain.
Oh man, blockchain.
Yeah, it is a major buzzword, often misunderstood, but the textbook provides a really solid foundational definition.
At its core, stripped of the hype, a blockchain is simply a digital public ledger. It is a specialized database that stores transactional data in discrete batches called blocks, and those blocks are chronologically and mathematically linked together to form a continuous chain.
The genius of the blockchain, and the reason it is considered incredibly secure, relies entirely on a cryptographic mechanism called a hash.
Let's break down the hash, because this is where the magic really happens. Think of a hash as a unique digital fingerprint generated by a mathematical algorithm.
Okay.
If you run a specific set of data through the algorithm, it generates a unique string of characters. If you alter even a single comma in that data and run it again, it generates a completely different fingerprint.
In a blockchain, every single block contains 3 vital pieces of information: a batch of recent timestamp transactions, its own newly generated unique hash, and crucially, the exact hash fingerprint of the block that immediately preceded it.
They are mathematically concatenated. Because block number 100 contains the fingerprint of block 99, they are permanently interlocked.
This is what creates the unalterable security. Imagine a hacker tries to go back in time and secretly alter a transaction recorded in block 50 to steal money. The moment they change the data in block 50, its hash fingerprint instantly changes.
But block 51 is still looking for the old fingerprint.
Exactly.
Because the fingerprints no longer match, the connection breaks. The discrepancy immediately alerts the entire decentralized network of computers verifying the ledger that tampering has occurred. The network rejects the altered block. To successfully hack the chain, you would have to simultaneously alter the data in block 50 and recalculate the hash for block 51, 52, 53, and every subsequent block, faster than the rest of the global network can add new blocks.
Which is computationally near impossible.
Right.
So the operational process is elegantly simple. A transaction occurs between 2 parties. That transaction is broadcast to the decentralized network of computers. The network mathematically verifies the transaction. It is bundled into a block with the digital signatures of the parties. The new hash is generated sealing the block, and it is permanently appended to the chain.
Everyone immediately associates blockchain with cryptocurrency, but I really want to look at the enterprise business applications first. Why does a supply chain manager care about a distributed cryptographic ledger?
They care because it provides unalterable, perfectly verified traceability. In modern manufacturing, supply chains are staggeringly complex. If a consumer electronics company discovers a defective microchip causing batteries to catch fire, they face a massive recall.
Oh, that's a nightmare.
With a traditional fragmented database, tracing that chip is nearly impossible.
But if the supply chain runs on a blockchain ledger, every single movement of that chip, from the mining of the silicon to the fabrication plant in Taiwan to the cargo ship to the final assembly line, it was all recorded as a verified, unalterable block. The manager can instantly and accurately trace the exact origin of the defective batch, isolating the problem to a specific factory on a specific day, saving millions in recall costs.
It is unparalleled quality assurance. We also see blockchain deployed for smart contracts. These are self-executing contracts where the terms of the agreement are written directly into the code on the blockchain.
How does that work in practice?
Well, when a shipment arrives and is verified by a scanner, the smart contract automatically releases the payment to the vendor without requiring a human accountant to authorize the transfer. It streamlines corporate auditing because the financial records are demonstrably accurate and immutable.
But we cannot ignore the most famous application, cryptocurrency. These are digital currencies that exist entirely natively on these network ledgers, completely bypassing central intermediaries like the Federal Reserve or traditional commercial banks.
And the creation of new cryptocurrency and the securing of the ledger relies on a process called mining.
Mining is a terrible metaphor, honestly, because it implies digging something up. Mining is actually the process of utilizing heavy-duty, specialized computer hardware to solve incredibly complex mathematical puzzles. The computers compete to solve the puzzle first. The winner gets the right to confirm the next block of pending transactions and secure them onto the digital ledger. In exchange for providing that massive computing power and electricity to maintain the network's consensus mechanism, the system algorithmically rewards the miner with newly minted cryptocurrency.
The landscape is dominated by a few major protocols. Bitcoin, introduced in 2008, remains the largest and most widely traded. Its corporate adoption is growing, with major retailers like Starbucks and Whole Foods integrating it into their payment systems. Then you have Ethereum, which differentiates itself not just as a currency, but as the primary global platform for executing those smart contracts we just discussed.
The text also brings up an interesting structural phenomenon called a fork, using Bitcoin Cash as an example.
Right, so because blockchains are decentralized, there is no CEO to make executive decisions. If the community of developers and miners fundamentally disagrees on how to upgrade the underlying software protocol, the network physically splits into two separate chains. This is a fork.
So in this instance, the parent chain, Bitcoin, retained its original parameters. But a faction wanted to process transactions faster, so they instituted a technological enhancement, basically increasing the block size capacity. That child chain split off and became Bitcoin Cash, operating as an entirely separate cryptocurrency.
Exactly.
It really highlights the chaotic, consensus-driven nature of this technology.
It is a fascinating frontier. But if we pull back from the bleeding edge of crypto and look at the daily reality of managing a business, we have to look at how teams actually leverage these networks to accomplish daily tasks. This relies on collaboration software.
Collaboration software is broadly defined as software designed to enhance the productivity of groups, and it relies entirely on the cloud infrastructure we discussed earlier. It is fundamentally replacing traditional management structures by natively supporting the four core functions of management: planning, organizing, leading, and controlling.
It bridges the gap between remote and in-office employees, streamlining workflows and centralizing communication away from the siloed inbox of traditional email. The textbook highlights three prominent platforms that illustrate different approaches.
The first is Smartsheet. To the untrained eye, Smartsheet looks exactly like Microsoft Excel. True. But while Excel is a static document, Smartsheet is a highly collaborative, cloud-based project management tool. It allows managers to assign tasks, set automated alerts for approaching deadlines, and integrate web forms directly into the spreadsheet to gather data dynamically from external teams.
A completely different approach is Slack, which is designed to largely replace internal corporate email. It operates as a channel-based communication hub. Teams create specific channels for distinct projects or departments, allowing for real-time chat, file sharing, and seamless integration with thousands of other enterprise applications.
And the third is Trello. Trello relies on a highly visual board representation, heavily borrowing from the Kanban methodology used in lean manufacturing.
I love Trello boards.
Yeah, you create visual cards for tasks and move them across columns representing different stages of a workflow process, like to do, in progress, and completed. It allows a manager to look at a screen and instantly grasp exactly what is being worked on, who is responsible, and where the bottlenecks are in real time.
These tools are how human capital organizes on the network. But as we move into the final phase of our deep dive, we have to address the reality that human capital is increasingly being augmented or entirely replaced by artificial intelligence.
Oh boy.
The integration of AI with computer networks and the internet is the fastest changing dynamic in IT management.
AI is no longer just a chatbot writing emails, right? It is actively embedded in the infrastructure. We are seeing the automation of the network itself. AI algorithms are currently deployed to handle repetitive network configuration tasks, More impressively, they analyze massive streams of network performance data to predict hardware failures before they actually occur.
Right. Predictive maintenance.
They can detect a router that is beginning to degrade and reroute traffic around it before it crashes, drastically improving uptime and reducing the labor costs of manual network maintenance.
And the impact on network security is even more profound. We must connect this back to our Module 5 cybersecurity discussion. We rely on SOAR, security orchestration, automation, and response.
How does SOAR functionally operate differently than, say, a traditional firewall?
A firewall just blocks known bad IP addresses. SOAR utilizes AI algorithms to constantly monitor internal network traffic and establish a baseline of normal behavior for every single employee.
So it is actively looking for behavioral anomalies. Like if an employee in the marketing department, who usually only accesses a few megabytes of presentation files, suddenly begins downloading gigabytes of highly sensitive customer data from the proprietary private cloud at 3:00 a.m., the AI flags that as a severe anomaly.
Exactly. And because it is an automated response system, the AI doesn't wait for a human security analyst to wake up and review the logs. The AI executes a real-time automated response, severing that user's network access and locking their account within milliseconds.
Wow.
That potentially mitigates a devastating insider threat or ransomware deployment before the damage is even done.
AI is also fundamentally changing how networks are architected from the ground up through intent-based networking.
Historically, if a business wanted to prioritize a specific application, a network engineer had to manually write complex configuration codes into every single router across the WAN. With intent-based networking, a manager simply defines the overarching business intent in plain language.
So they just talk to the system.
Pretty much. They instruct the system. Ensure our enterprise video conferencing software always receives the highest priority bandwidth over general web browsing.
And the AI just translates that high-level intent into technical configurations and automatically deploys the necessary protocols across the entire global network architecture.
Yep.
It also utilizes predictive analytics for capacity forecasting, analyzing historical data trends to tell management exactly when they need to purchase more bandwidth before the network becomes congested.
But, as these networks scale, sending every piece of data back to a centralized cloud for the AI to process creates the exact latency issue we discussed earlier with 5G. This is driving the development of intelligent edge networks.
Okay, so if the latency of sending data from a factory robot to a centralized cloud in Virginia and back is too slow, the architecture has to change. Edge computing literally moves the data storage and the AI processing power physically closer to the user, out to the edge of the network.
In an intelligent edge network, that smart factory installs local, highly powerful AI servers on-premise. The robotic sensors feed data directly to the local hub. The local AI processes the data and makes autonomous manufacturing decisions in milliseconds, completely eliminating the latency of relying on a distant central cloud.
That covers the hardware side. But what about generative AI, the large language models that have basically taken over the business world? How do they interact with the internet infrastructure?
Generative AI is entirely reliant on the internet for its raw material. These models are built through web scraping, deploying automated bots to traverse the internet, extracting trillions of words from websites, books, and articles to serve as training data.
But traditionally, this created a severe limitation.
Yeah.
The knowledge cutoff date. If a model was trained on data up to 2024, it knew absolutely nothing about events in 2025.
Which makes it totally useless for real-time business intelligence. But the industry is solving this through a process called raw RAG retrieval augmented generation.
Let's dissect RJ because it is a vital concept. When you prompt a RAG-enabled AI model with a question about current market conditions, it doesn't just rely on its static training data. It actively reaches out to external, live sources on the internet in real time.
Right.
It queries current news feeds, live financial databases, and corporate APIs, retrieves that up-to-the-minute factual data, brings it back, and uses it to augment its generated response. RJ effectively solves the knowledge cutoff problem, making the AI highly accurate and actionable for managers.
To bring this all full circle, the sheer computational demand of training these AI models and running global cloud infrastructure is pushing the physical limits of the internet. We are closing out this deep dive by looking at how AI is deployed to basically save the internet from itself.
Yeah, the demand on hyperscale data centers is staggering. AI is heavily utilized for network load balancing, or NLB.
Yeah.
It dynamically analyzes global traffic patterns and intelligently routes data packets to servers with available capacity, ensuring no single data center is overwhelmed.
Furthermore, AI is critical for managing the massive energy consumption of these facilities. Data centers generate immense heat. AI algorithms constantly monitor internal thermal sensors, dynamically adjusting cooling systems, routing power only where needed, and shifting computational loads to servers in cooler climates during peak hours.
That's incredibly smart.
It makes the physical infrastructure of the internet significantly more energy efficient, sustainable, and cost-effective.
Wow, we have mapped the entire architecture today, from the PAN connecting your headphones, through the LANs and WANs, up to the ISP gateways routing dynamic IP addresses across the global internet backbone using TCP/IP protocols.
We covered a lot of ground.
We explore the HTTP and HTML mechanics of the web, trace the evolution from Web 2.0 Folksonomies to Web 3.0 Ubiquitous Computing, and mapped out how 5G limits latency for the IoT.
We analyzed the economic multiplier of cloud computing across its deployment models and services, secured remote connections with VPNs, explored the cryptographic hash securing the blockchain ledger, streamlined our workflows with collaboration software, and finally examined how AI is actively designing, securing, and optimizing the very networks it runs on.
Understanding these interconnected systems is not just an IT requirement. It is the ultimate prerequisite for modern business leadership. You cannot effectively manage an organization if you do not comprehend the digital infrastructure it relies upon to function.
That is the absolute truth.
Thank you so much for joining us on this extensive deep dive into Module 6. Before you log off, please remember to like, subscribe, follow, and share the deep dive. And we specifically want you to head down to the comment section right now because we have a strategic scenario for you to solve based on the frameworks we just discussed.
Here's the scenario. Imagine you are newly hired as the IT manager for a medium-sized web development firm. You have 150 employees, all of whom are entirely remote, scattered across the United States. Your firm handles highly sensitive proprietary data for Fortune 500 clients every single day.
Based entirely on the concepts from today's deep dive, here is the discussion question. Would you recommend your company utilize a public cloud, a private cloud, or a hybrid cloud environment to host this data? Furthermore, which specific service model, SaaS, PaaS, or IaaS, would be most critical to provision for your developers to build applications efficiently? Drop your specific architectural strategy and your management reasoning in the comments below. We read and respond to every single one.
As for what comes next, well, today we laid the cables, built the data centers, and secured the connections.
Next time, we take all this incredibly powerful network infrastructure and finally put it to work for the enterprise. Join us for Module 7 as we explore business management systems, uncovering how global corporations utilize massive enterprise software suites to actually run their day-to-day empires.
It is the natural culmination of everything we have built today.
You won't want to miss it.
Yeah.
But before we sign off, consider this final thought to chew on. We talked extensively today about how secure data is when it travels through encrypted VPN tunnels, or how uncrackable a blockchain hash is because it is mathematically near impossible to solve.
Right.
But that security relies entirely on the limitations of current computer processors. We are standing on the edge of the quantum computing era. Quantum processors operate on completely different laws of physics, performing complex calculations exponentially faster than anything that exists today. The moment a functional large-scale quantum computer comes online, the complex cryptography securing those VPN tunnels and the uncrackable hashes locking the global blockchain ledgers could potentially be shattered in seconds. The very networks we trust today might become utterly transparent tomorrow. Until next time, stay curious.